Hello, everyone.
Most of the support's actually in a feature branch already. And so I have documented, for example, some default implementations for some of these. So in the previous review, this was just static abstract, and now it's actually documenting that we're going to provide a default implementation for check plus where it has the same behavior as operator plus. And if a given type desires a difference in check behavior, then they should explicitly override that. Um, but in general, that's just documented. Um, my preference is that we don't, for example, have not equals implicitly override, have an implicit implementation, um, just because um, that would be unique kind of to these operator interfaces. And this is something where you often want to provide two differing implementations for perf reasons with these numeric types anyways. Um, but the rest of these interfaces haven't changed at all for those, nor have the additive identity, min-max value, or multiplicative identity. Um, uh, Likewise, the function interfaces haven't changed. They still just have them. There is a documentation for providing dims for the -1 functions on exponential. Uh, that isn't as accurate as it could be, but the contract for these functions isn't necessarily a 100% accurate result. Some types may decide to just provide a performance or convenience implementation, whereas other types may decide to provide more accuracy where that's relevant. Um, Likewise for log +1, default implementation provided. Then we get to the core numerics interfaces, which likewise haven't had too many changes. The biggest change for ibinary integer is shift operators now support the right-hand side being something other than int. .NET historically has only allowed int there as far as C# code has been concerned. And so there's kind of an open question here, which I'll let API review discuss a little bit here on should we, for convenience, also require binary integers, implement the int version, or should we say only tself? Jeremy?
You seem to be going through a list of things, but what's sharing in Teams, you're still at the top of the document. Are you scrolling?
Imo, is it not? Are you showing your screen instead of mine?
No, it's your screen presenting. I also see just the top of the document.
Maybe I've got two windows open.
I've never made that mistake. Wow, that looks much more.
Does it actually show? Is it scrolling in
yes,
YouTube?
We can see your selection. We can see your scrolling. I mean, YouTube is delayed, right? So if you look at YouTube, you'll probably see from like.
Okay, so just to go back on what I covered, most of these haven't changed. For some of these interfaces, like iAddition operators, I've now explicitly documented where a dim will be provided. For these, it's specifically that the checked variant will default to the same implementation as the unchecked variant. Types where they want both checked and unchecked behavior will be able to override this and provide it where applicable. And then likewise for the exponential functions, log plus 1, and then that's where we got to here. Any questions or needing me to recover something which wasn't visible since it wasn't scrolling before? Okay. So the question being that historically C# has required that the right-hand side be int. Should we, for convenience of users who may continue to expect the right-hand side be int, and for the case where they are shifting by a literal, should we allow or require binary integer to provide both the tself and the int version? That way, we kind of have paths for both the existing familiar syntax and the newer syntax where you may have, in fact, a tself from other operations, and doing the required conversions, etc., may be too costly or expensive. Any input?
I mean, is that one being provided with the virtual, or is it being required as a mandatory implementation?
We would be able to provide it with a default implementation where it's functionally deferring to the tself version via the create checked call. So we could provide a dim so that users are only required to implement it if they want additional performance there.
Yeah, I mean, if the language has previously required that if you overrode the operator, you can only have it be with int, then that seems like there'll be places that would just light up with that for consistency, and I don't see a strong reason not to.
Okay. DivRem was notably moved off of number and up to ibinary integer. The reason for this is that the behavior of DivRem in context of floating point numbers is potentially confusing because it doesn't actually perform the equivalent of division and remainder. It instead performs functionally what is closer to mod f for floating point types, where it performs a division truncating the result to the nearest integer, multiplying that back and getting the integer remainder out. And of course, with floating point, normal division doesn't have any remainder. It just returns the fractional quotient. So this was moved up. There's a long note here for leading zero count, pop count, rotate left, rotate right, and trailing zero count, covering the behavior in the context of variable size types, such as native int, where it's 32 bits on one platform and 64 bits on another platform, and types like big integer, where the type doesn't have a fixed width and is instead variable width. This is basically just explaining that the functions are effectively in terms of get byte count times 8 bits. And so if your big integer is represented via 3 units under the hood, that's 96 bits, then get byte count would return 12. And then your actual bit count would be in terms of 96 bits. And so the leading zero count is out of that 96 bits, not the theoretical maximum bit length of a big integer. This also then functionally represents the same operation that occurs for fixed width types and for the variable width types like native integer, which differ on platforms. So it's mostly just documenting what that contract is in the case of variable size types. There's a new API proposal here that we expose reverse Endianness. That way you can actually perform a relevant byte swap for your 2's complement integer if that's appropriate.
Is the assumption that everything would already be machine Indian? Like it's weird to say reverse Endianness if you don't know what the Endianness is.
Yeah, the assumption is that types are in machine Indian format. If we believe that types should be in whatever Endianness that they want to be in, then we could additionally expose some is little Endian or is big Endian properties. That way users can query what format it's interpreted as.
What would that do for like int32? It would just always return true?
Is little Endian would return true on little Endian platforms and false on big Endian platforms.
Right, but then it's weird if you call reverse Endian, it still returns the same value.
Right, it would reverse the Endianness from whatever the current Endianness is.
Right, but then it wouldn't know, like, is little wouldn't start returning false. So that's pretty weird.
Yeah.
Right. Well, because now if you do addition with it, it's representing a different value. But, I don't know. That one seems.
I can kind of half see the utility if you're doing something like, you know, binary writer, things like that, like where you just want it to be able to take any arbitrary width integer. Like this would allow you to implement that in order to do, you know, host to network order.
But that feels like you don't want reverse Endianness because that comes back to what Endianness is it. You want, you know, export methods of go write down the bytes of yourself as a big Endian or go write down the bytes of yourself as a little Endian. Like it's weird to talk about the Endianness of this is a number with a numbered reverse Endianness. Like that doesn't make sense to me. Import export, sure, but T-self to T-self doesn't. To me, this doesn't make sense.
See.
Okay. So you would prefer that instead of having reverse Endianness and just the, for example, try write little Endian APIs, instead have both try write little and try write big.
Yes.
Okay.
Was that the use case for which this was proposed, Tanner?
Yeah, it was more generally being able to take an existing number type and swap the bit order.
Right, but I mean, like, what do they then do with it? Yeah.
Generally, some form of getting the most significant byte, or least significant byte out of it. So the primary use case is with the write little Endian API, and having a write big Endian API is more surface area, but likely also more performant.
And much better intent, and doesn't clear. I mean, I agree that if you have a value and you say go write yourself as some bytes, and then you say reverse Endianness and you say write yourself as some bytes, you now have theoretically a little Endian and a big Endian value. You just don't necessarily know which is which. So having the methods just say write yourself as little Endian or write yourself as big Endian make much more sense to me.
Okay.
Yeah, I guess that kind of makes sense, because all of these are really intended, like it seems like these types are really intended to represent the abstract notion of a number, where the actual representation in memory is kind of ill-defined. And Endianness, like Jeremy said, really only makes sense when you care about projecting it as raw binary representation.
Yes.
I mean, it is binary integer, to be fair. Yeah,
there is some presumption that users are going to have these be 2's complement integers, not 1's complement, and that they're going to likely be in little Endian format, because that is the most prevalent format for number types across the entire ecosystem. But if we wanted to theoretically support more underlying formats more readily, we could surely just not have this API and instead have the try write big Endian to make that that bit a little bit more abstract. We then get to the byte count and shortest bit length APIs, and then the try write little Endian, write little Endian, with these three having default implementations that do the de facto thing. There is so with the reverse Endianness decision, this would just expand to having 4 more methods that are just write big Endian, and try write big Endian. There is a somewhat existing consideration for these APIs that came up last Thursday, which is that for a case like big integer, there's kind of two things you might want to consider. One, a big integer might have more than array.maxLength bytes in it, because it might, for example, be represented by a uint array under the covers. Likewise, when using these APIs, you may only want a subsection of the underlying representation. That is, for example, consider you're converting a big integer to an int32 via truncation, using these write APIs, because you're not directly supporting the target type. You only need 4 of those bytes to successfully truncate. You need the 4 least significant bytes. And so in that case, it would be beneficial if we had some sort of chunking API here. Effectively, I don't have a good name for it, but you would effectively have try write little Endian API that takes a span destination and a int start byte, which is between 0 and byte count in value. That would allow you to effectively read the next in bytes out of the underlying buffer.
I mean, in the case of Big Endian, if you want only the bottom 32 bits, just mask it, and now you have a smaller Big Endian, or a smaller big integer.
That is potentially a very expensive operation depending on the type. The one of the considerations for generic math is you don't know what the T is. So you don't know you don't necessarily know how to efficiently get just the lowest 4 bytes, and that could be masking against max value, against int.max value converted to the type, but that conversion, that mask, etc., could potentially be expensive. In which case it would be more beneficial to have a way to chunk the APIs, which then also covers the scenario of my backing buffer contains more than max length bytes because it's represented using int or long, for example. But we do not have.
I mean, again, but now you need, partial big and partial little Endian, and then you have the notions of, should people be counting from the most significant byte or the least significant byte, and like it just. Yeah, I think it would have to be designed, and it's probably a 30 or 40 minute argument all by itself.
Right. We don't have an existing syntax or area for it, which is why it's kind of not covered here. But I did want to bring it up as something where it is a consideration we have. It is something that would be nice to have, but is not critical to have. And it's potentially something we might want to discuss more in depth for how that would be exposed if we should expose it. But potentially as a future design item there.
Tanner, so what we're seeing on the screen right now with regard to like write little Endian, write big Endian, are these default interface methods that we're seeing here, or are these just like we don't anticipate anybody ever giving more efficient implementations of, say, the byte array, int overload?
Correct, because they're required to implement the span one, and these should all have the same implementation. And so these should functionally be the same. Users should never end up effectively there is no more efficient implementation someone could have over the span implementation.
Okay. So we would never expect anybody to implement the byte array variants, for instance. Like, from what I'm seeing on the screens, could somebody do it if they were so inspired? Like, is that an extensibility point we offer?
I think that is an existing extensibility point because instance methods on interfaces are virtual by default unless you explicitly declare them sealed.
Okay. So by virtue of the fact that they're on the interface, you could, if you were truly inspired, do it. Okay.
Yeah.
Great.
But the expectation is no one should need to.
Sure. I guess one of the things that I'm kind of getting at is it would be interesting from a usability perspective to see if people, kind of like how when you're overriding stream methods, to see if people realize exactly what methods they actually need to implement and what's just give them a good default behavior.
Yeah. In this case, we'll likely want an analyzer over time, I think, by default with there being nothing. And then in the future, if we add new implementations to kind of flag things where, hey, this implementation may be less efficient because it's a dim, which has to fall back to something that's non-optimal. But in most cases, because of the way the interfaces are exposed, we are able to define correct and performant implementations. So moving forward, there's just a small annotation for ibinary number, which is that this the log2 on ibinary number conflicts. It doesn't actually conflict. Both get exposed, both are accessible. There's no ambiguities in what's available or anything else, but functionally there is both log2 here on ibinary number, which is used to support integral types, but it's also defined on iLogarithmic functions, which, for example, might be exposed on complex. And so it's just a note that there's two methods with the same name that are expected to have the same behavior there across two different interfaces. The idecimal floating point IEEE function is not important because we don't currently define decimal IEEE floating point types, but it is listed here for kind of consideration as what that would look like in the future. iFloating point contains the ceiling, floor, round methods. It likewise contains APIs to get the exponent and significand out. Much like binary integer has the right little endian APIs that gets the 2's complement representation of the value, this gets you the 2's complement representation of the exponent and significand. And so given the reverse endian decision earlier, these would likely also have big endian variants.
Quick question on stuff like this. I see that the get byte count APIs are int and the get bit count APIs are long. Like, do we reasonably expect somebody to have a byte count that is measured in the 250 million bytes, such that get bit count would actually overflow?
So big integer currently exposes its get bit length API, that returning a long, because theoretically the implementation allows up to that. My belief is that unless they're backing this by native memory, in which case it's not feasible for them to have an array that big, just because of the of how it will negatively impact the GC and memory in general. Most users likely aren't going to have a 2 gigabyte backing struct.
Right, but I'm wondering if, for whatever reason, using long here would just make the APIs a little less usable because now everybody has to cast. Because I can't imagine any type ever in the entirety of, let's say that .NET lives to be 100 years old. I'm having trouble imagining any numeric type ever that would require 250 megabytes to store a value.
Yeah, I think it's a case of where there's not much harm in allowing the long, and types which will never overflow. For example, I would like to restrict big integer to never being more than 256 megabytes. Mm-hmm. I think they can do the optimal thing, but I don't think we should necessarily restrict HPC, high performance computing scenarios, or ML scenarios where devs may actually have or be working with really big numbers that can grow that large, potentially backed by native memory.
Sure, and I can see the theoretical aspect of it, but realistically, that means that anybody calling these APIs has to have some kind of policy in place for what happens if this number overflows into 32. Their policy might be we simply cast it down to int and ignore all the high bits, and maybe that's good, but that seems like something that they should, have taken into consideration when they did that cast.
If API review as a whole believes that it is better to say that all number types in .NET must be restricted to no more than 2 gigabytes of bits, I believe I would be willing to accept that.
I mean, even crypto numbers currently stop out at about 16 kilobit numbers. So 2 gigabit numbers feel ludicrous speed. So, yeah, I agree with Levi. The most common callers of this are just going to be unchecked cast to int. So we should just make it int, and when we need a I bigger number type, we can make it.
Yep, that sounds fine to me. That also goes in line with what I'm already trying to push big integer towards, because it massively simplifies the logic and considerations there.
Yeah, and if there are theoretical scenarios that end up being hit by that, like definitely, make comments to that effect. But I'm just having trouble wrapping my mind around the whole, like, we now need to make every single caller on the planet take into account the fact that there might, in some far-flung future, maybe, perhaps, be a theoretical type that does this.
Yep.
And that's just a pit of failure.
Yep, and that's also kind of why why byte count is restricted to int, because we're taking in a span here, and unless we're planning on changing the backing length of span to be native int, like, and there are people who want that, there's no reasonable expectation for this to be more than that byte count. It also simplifies the chunking decision a bit, because there would be no chunking consideration. We effectively say all types must fit within 2 billion bytes, if you're considering it as a coherent number. Or let's not say any number, but any scalar value.
Sure.
What's the difference?
You might have something like rational or complex, which are represented by 2 scalar values. And so the sum of both scalars might be, for example, 4 billion bytes, but each individual scalar will be no more than 2.
Gotcha. Thank you.
We then get to the I floating point, IEEE 754 type. Oh, sorry. One other call out. The previous review name for this was get significant bit length. I found that confusing, and so I explicitly inserted the word shortest here to help clarify that this is the shortest 2's complement bit length representation of that value. So for example, -1 always returns 1 bit. You require 1 bit to represent -1, because it is effectively the sign bit and then extended out to the full length.
And so this is the answer from this tells you what the minimum size span is for the equivalent try, right?
It tells you what's the so let's say that you have, for example, an int 64, and you want to know, can I convert this to an S byte? Well, the values between -128 and 127 can be represented, and so provided that get shortest bit length is less than or equal to 8, then it is a value that can fit into an S byte. And so this allows you to determine, regardless of what the underlying bit representation is. For example, -2 as a int 64 uses all 64 bits, where you've got the first 63 as 1, and then the last bit as 0. It allows you to determine what is the shortest way to represent this value as a 2's complement number, and that's 2 bits required. And so you know that -2 requiring 2 bits will fit into an S byte, for example.
Does this also mean that +1 would require 2 bits because it requires a leading 0 to disambiguate the 2's complement aspect?
No, it still requires 1 bit. Because unsigned numbers do not have a sign.
Yeah, but I mean, if the type is signed signed variable length integer.
Right. There are APIs is negative that allow you to determine whether the value is positive or negative. So you have to use in coordination both the bit count and that check, because otherwise you'd have 255 returning 9, which means that you still have an ambiguity of whether or not that can fit into a byte. And so you have to use this API in coordination with is positive or is negative to determine will it fit.
Got it. So this is really like how many digits follow the first one if it exists.
Mm-hmm.
Okay.
As per last API review, the IEEE floating point types are in iFloating point IEEE 754. They are a floating point type that explicitly provide the IEEE required functions. We have several properties covering the constants. We've got the bit decrement and bit increment, fuse, multiply, add, and a few other IEEE specific functions. And then we have a call out kind of over some of the IEEE required functions that aren't exactly covered by .NET today. So round integral is covered by round. That's fully there. Convert to integer is an interesting case where we have, via the APIs exposed, the ability to cover these and cover them compliantly, but we don't have direct APIs to cover them because unlike C, we don't have a way to set the integer rounding mode directly. Convert from and to hex characters are covered by toString and parse. Compare we have covered via the comparison operators. There is a special type of function called unordered, which returns true if either input is nan, which we don't support today. And I'm not currently proposing that we support those either. I just want to explicitly call out the consideration around the IEEE support here. IEEE does request that you expose properties indicating what effectively spec version you're compliant with. We don't expose those anywhere in .NET today. We theoretically could just expose a public static bool is 754 version 2019 or similar, and just have a default implementation that returns true, since this interface does follow that standard. But I don't have a preference on if we did that or not. There is a classification function, which is effectively a way to query multiple is methods simultaneously and return an enumeration value. We don't support that today, nor do we support the total order functions, which they're similar to iComparable, where it actually defines a behavior for nan, but it's also a little bit different from how compare works today. Namely in that it actually treats -0 as not equal to +0. And it requires that negative nan be lesser than everything and positive nan be greater than everything. So that's an area where there is an IEEE recommendation we expose a way to do total ordered comparison, and where neither the regular comparison functions follow that, nor do the iComparable compare to. And then there's a call out of there's some recommended functions but not required functions covering kind of reduction. These are, some is covered by link somewhat today. Some of these other ones we may want to consider for link in the future, but I don't believe we should expose on the generic math APIs. And the same goes for the augmented addition, subtraction, multiplication. It effectively just has a different default rounding mode and lets you accumulate what the rounding error is across many operations, which is useful for various scenarios. But it's not something that we should require be exposed on the IEEE functions today, particularly since it's not required by the spec. Any questions?
I mean, my general question is like, is there any downside with exposing optional things on these kind of interfaces? Do we want them to represent what's required by the spec, or do we want them to represent what's useful?
Both. So for the most part, we want to ensure that we're spec compliant with IEEE. Just because that allows us to, claim IEEE compliance, allows developers to correctly work with floating point types and meet all their usage scenarios and needs. So particularly where there's a required operation, it's beneficial to provide. There are a few cases where we've explicitly decided, particularly where it is allowed by the spec, to have a different behavior. For example, we explicitly do not support IEEE floating point exceptions. We explicitly, therefore, also do not support signaling not a numbers. And so, with what's proposed above, except for the classification and the total ordering APIs, we are effectively compliant.
Yeah, I was more asking like what, I mean, with .NET Standard, we kind of had this view that this is basically the specification that platforms have to implement, right? So if we port this, to a new runtime environment, right, a new CPU, would there be a downside of saying, we can support most of the interfaces except the 4 optional ones that we added, or the optional ones always implementable given the required APIs that are already on there?
They're always implementable given the required APIs that are on there.
So we can basically, we can always exceed effectively what's required by the spec. And there's
right. And for these ones that aren't covered in today's proposal, which are more just call outs here in the sub notes, we could provide them as dim implementations in the future because of that.
Do you foresee any example where we cannot implement a certain numeric type at all?
Not from what I've seen today. And as we get further down, we start seeing more and more examples, especially on the base types like iNumber, where default implementations are provided for many of the functions because they are well definable in terms of other functions. And so the subset that you actually have to implement is increasingly small. And it mostly becomes I want to override the behavior, such as I want to provide checked support explicitly, or I want to provide a more performant implementation where you have to actually go and do a more concrete implementation.
We have no cases like hardware intrinsics where you would have to query whether something is supported and it might blow up. It will always work, it just might be slower, right?
Right. As far as I've tried to design these, that is the case. There's certainly potential on iNumber base in particular, where there may be scenarios just because of how differing real numbers are from complex numbers, for example, that we could end up in such a scenario where you need to query for support in the future. But I've explicitly tried to ensure that these are set up in a way that that requirement is minimal. We then get to iNumber, which is effectively a iNumber base, but it's also comparable. It is also iSpan parsable, whereas iNumber base is not. There was an open question last review on whether we should move span parsable down to iNumber base. And there's kind of two thinkings there. One is that you can, in fact, parse a string representation of any number type, including complex numbers. The other is that parsing some number types like complex numbers can be increasingly complex because a complex number is represented by 2 values. So you effectively need to either parse parentheses, a value, a comma, another value, and then a closing parenthesis, or you may need to parse, for example, an expression format depending on how you were to represent your value, etc. And so my leaning is, in fact, that all numbers are formatable, but only iNumber and below are considered parsable by default. But that's not a strong feeling.
Can you give me like
and
like an intuitive understanding, like what's the difference between iNumber and iNumber base?
iNumber is more meant for scalar-like values, where you have a single underlying value, or it can be represented as a single real number from the mathematical sense. So this could include even rational types, which might be represented by a numerator and a denominator, but which can still be represented as a single real number. Whereas something like iNumber base is explicitly meant to represent non-ordered numbers. So it includes things like complex numbers, which are actually represented by both a real and imaginary part. And because they are not ordered numbers, there are a lot of additional considerations and complexities that come about from them, particularly that they are more represented by an expression rather than by a single numeric value.
And so is that the rationale why you think they may not be able to parse by default?
Right, because not every user may want or be able to effectively support string parsing of what might be a complex expression representing the value. Although we could equally just say that users should, in fact, have a well-defined format for that and support parsing it. And then we can, and then it would be reasonable for users to actually go and do that.
I mean, I have a hard time imagining a world where you effectively have, went to all the trouble of having numbers, but then can't be bothered with parsing them, because it seems like you want to, you process inputs presumably, right? And ultimately they will come from something, right? And you want to probably toString them. And so at that point, you probably also want to parse them. Like I find it hard to believe that somebody would find that too difficult to implement.
Unless anyone else has other feedback, I will take that as move ispan parsable down to iNumber base, and then number types are expected to support both parsing and formatting.
I mean, presumably you can always cheat, right? You can always have like a parenthesis, right? And then you just match for the next parenthesis and then do a string split or something, right? I mean, you should always be able to define a format you can parse, right? You don't have to implement an expression parser.
Right. There should always be some form that you can define and support. Because this is comparable, there's a clamp function, which clamps the value between max and min. Much like math clamp does, it throws if min is greater than max. There are some people who would prefer that we not have this handling here, and we just define that this has a well-ordered behavior if min is greater than max, because that's what is most performant, and that's what, for example, hardware acceleration for clamp functions does. But I opted to default to matching what math clamp does today, so we don't have confusion on users. There is then a copy sign API. This one could theoretically move down to number base, but you get into kind of considerations of what does it mean for a value to copy the sign when it has multiple parts? Does that mean, for example, with complex, that you would copy the sign.real to value.real and sign.imaginary to value.imaginary? Or not, and so I opted to keep this on iNumber instead, particularly since once you start considering the concept of signedness, it gets somewhat confusing for complex numbers. There is the max function, which correctly handles nans, and likewise max number. And the reason that that max number, even though it only applies to floating point types, is on iNumber, is because most users will be constraining to, for example, iNumber. And it is not feasible or possible in C# or .NET today to do something like a if t is ibinary floating point, then you now have access to the static members available to ibinary floating point types. And so, for example, in link, where link max functionally operates as if it was doing max number, we want to ensure users have access to that functionality regardless of type. Functionally, the primitive integer types wouldn't expose this publicly. So byte.max would be available, but byte.maxNumber wouldn't be available. It would only be available in a generic context because it only makes sense in a generic context.
I have to ask a dumb question. I think we have covered this before, but I keep forgetting it. Like, why are we referring to these as T self and not just T?
Because the expectation is that the implementer is the type in the generic constraint, and that's actually a requirement for the constraints to work correctly. It's a recursive constraint, and so you can't define, for example, my struct implements iNumber of int. That is an invalid definition because generic constraints no longer function correctly. So we're explicitly documenting this is the type that implements the interface.
But isn't it the same as like things like, we have I-equatable of T? I mean, you usually, you could in principle implement it over something else, but that would be nonsensical.
T is functionally other in I-equatable. The T self is this as far as instance members are concerned. And so the T in I-equatable of T is actually T other. It is the other type you're comparing against. And there are people who go and define, for example, big integer, for example, while it doesn't implement I-comparable of int, it exposes a compare to int function. And so you have what is functionally an big integer implementing I-comparable of int and I-comparable of long and I-comparable of big integer. Even though it doesn't actually implement the former two interfaces, it just exposes the corresponding function.
But practically, like T self is like, usually a scalar, right? It's like int, float, whatever implements that interface, right? Unless you have a custom type, yeah.
Yeah.
So Tanner, looking at your implementation here for max number to figure out what max number does, I don't understand it, because if x is equal to y, why are you asking if something's negative? Because if x is equal to y, just return whatever.
Because you have to propagate -0. -0 for the purposes of max and max number is less than +0 by spec.
But it is equal?
Yes.
-0, okay.
-0 equals +0, but for the purposes of max and max number, it is considered lesser.
Of course.
Tanner, do you mind explaining again the difference between max and max number?
So max is required to propagate a nan. So if x, so if, for example, if you have max nan 5, it will always return nan. Whereas if you have max number nan 5, it will always return the 5. Max number returns the number type, whereas max is required to propagate the not a number type.
Can you point to the line of code that is the difference between these two? I'm struggling to find it. The difference in implementation.
I might have a copy paste error here.
Yeah, because I also noticed that the val1 and val2 should be the arguments to max, right?
Right. I think I just had a copy paste error here when copying the dim. The actual implementation we have right now is correct though in source.
Okay.
So I'll leave a note to fix that in the design doc.
Thanks.
Or just don't include implementation. You can never be wrong.
Yeah. We've got the parse APIs, which are going to move down. And then we've got the sign API, which works like math sign, and it returns -1 if the value is negative, +1 if the value is positive, and 0 if the value is 0. And this is a Framework 1.0 API.
So there's no negative, positive, null, or NaN?
No,
or...
there is. That's on number base here.
I see. Okay. That's way too easy.
Yeah. So iNumber base exposes absolute value, and the reason for this is because all numbers, including complex numbers, have an absolute value. The absolute value of a complex number is always a real number. And so while this does return T self, because we don't have associated types, and so therefore we can't define some norm or magnitude type, the imaginary part for a complex number returned here is always going to be 0. But it is well defined for all number types. This is an example implementation, an example dim implementation if this were on iNumber, but since it's on iNumber base and therefore applies to complex, it's not valid. We have 1 and 0 types. We also expose the radix, which is the base. So decimal would return 10, float and double, int, and other types would return 2. This is important when you're extracting, for example, the significand and the exponent, so you know how to construct the actual value out of that. Radix is the mathematical and industry standard term for this in other languages. And of course, base is just a bad name in general, which is the other name people refer to it as by.
So for the try parses, it didn't look like you were suggesting any of them would be dimmed. It seems like those could be.
Yeah, we likely could provide them as dim with the string version, doing the relevant null check, and then deferring to the span
one, and then it seems like parse could just defer to try parse. So really, the only one that you'd have to write would be the fourth one.
Yes, I believe so.
And you could write others if you had reasons to, but the fourth one should be the only one required.
Right. I'll leave a note to add that to the design doc. So the create APIs were moved down. I'm actually going to skip the create APIs momentarily, cover the rest of it, and come back to the create APIs, because the create APIs actually have an entire section below covering them and why they are designed the way they are. These is checks are potentially the most core and critical APIs that help allow the rest of the number types to be implemented correctly and efficiently. So we have is canonical, which means is this the canonical representation of that value? This is an IEEE 754 concept, but it also applies to decimal, for example. This effectively means, is this the canonical representation of the value? So for example, decimal has multiple representations of 0. You have 0, 0.0, 0.00, etc. Depending on what your specified base 10 exponent is. So is canonical would effectively return true if this was 0 or 0.0, depending on what we defined it as. And not if it was any other representation, which is important for understanding, is this representation effectively already in its most optimal form or not? We have is even, and I've actually explicitly called this is even integer to help clarify what the behavior is for floating point types. So 1.0 would return true, whereas 1.1 would return, or 2.0 would return true and 2.1 would return false, because numbers that are not exact integers are neither even nor odd. And so it's important that people understand that this is only if it's an even integer. If it is, and so both is even integer and is odd integer could return false. And that's also why we have both present. One, because it's somewhat confusing to have to consider negations in complex statements, but also because both is even and is odd could return false for certain types. This is a existing property that we expose on big integer, and it's effectively required so that you can have an efficient implementation, because you may not know if ANDing a result with 1 or even doing mod of a number with 1 would correctly return whether it's even or odd. We have the query APIs that exist on floating point types. So is it finite, is infinity, is nan. We have is integer, which will return if it's an exact integer or not. We have is negative, and likewise is positive. This is important because complex numbers may not, if they have an imaginary part, be considered positive or negative because there is ordering for them. So you cannot strictly define if it is less than 0 or greater than 0.
Do we already have notions of positive and negative in the BCL?
We have concept of is negative in a couple places, like negative infinity, negative 0.
The reason I ask is 0 is not positive, it's also not negative.
For the purposes of the way most of our APIs work and the way that the IEEE functionality is required to work, 0 is considered positive if it is a positive 0 and negative if it is a negative 0.
Fair enough.
And if there is no sign on the 0, it is considered positive by default.
Yeah, the 0 case is why I was asking if we have prior art in the BCL.
Yeah, and that would explicitly be around is negative for the floating point type, which covers positive and negative 0.
Jeremy, to your question, are you looking for a method which is non-negative?
I'm just, he has the dim implementation of is positive is not is negative, and I'm wondering if we've elsewhere used is positive to mean is greater than 0. Because if that's the case, then this dim is wrong.
Yeah. As far as the IEEE required implementation is, this is correct. In terms of complex numbers, this actually shouldn't have a dim at all, because complex numbers may not be considered positive. So this is a copy paste here, and it shouldn't have a dim anymore. That was from when I still had it on iNumber.
So it should be fully abstract, is what you're saying?
Yes.
Okay.
We have is signaling nan, is subnormal, is 0. There is also a question of should we provide is complex number and is real number just to satisfy the scenario of determining does this have an imaginary part or not. I would lean towards yes, we should provide those, but it's not a strong preference.
How would you extract the components back out of it?
So for complex numbers, you wouldn't today. There's a section later in the doc that covers we should likely expose an iComplex number interface, which inherits from iNumber in the future, but which is out of scope for .NET 7.
I see. So if we had such an interface in the future, then we could have an API which is like has complex part or something like that.
It would the iComplex interface would likely directly expose a T-scalar real and T-scale imaginary.
Okay.
Yeah, for what it's worth, it looks like there's a SQL decimal type that has had a is positive, and it defines 0 to be positive. So we do have prior art of is positive having that behavior on 0.
Okay. We have on iNumber base max magnitude. max magnitude number, min magnitude, and mid magnitude number. The reason that these can be defined on iNumber base, even though complex numbers don't have order, is again because all numbers, including complex numbers, have a real absolute value, and the comparison is done in terms of the real absolute value. And so you can do a max magnitude for two complex numbers because it will compare the comparable the real absolute value to determine whether the complex X or Y should be returned. And again, it's got a commented out implementation for what the real number implementation, but which can't be provided for complex number types implementation would be. And then skipping over the conversion and create APIs. We have iSign number, which has -1, and then iSign number base, which is largely a marker interface, but which is required to be implemented on number types. And this iSign number interface exists as it documents because it's impossible to check for a lack of an interface and a constraint. So if you want to restrict only to unsigned inputs, you require such an interface to do that.
Just to clarify, like there's no concept of a type traits like given some t, get the unsigned integer that would be equivalent width to this t.
Right.
Correct?
We
like
don't,
that's not something we're doing. Okay.
We don't have associated types.
Okay.
And also skipping iNumber converter just because it's part of the conversion APIs. We then have covered the numeric interfaces, and it's mostly just now a giant list of what the primitive types and how they're going to implement them. There is an open question for the primitive types. So today we expose max value and min value, their existing APIs as I've documented. For types like big integer, decimal, what we're going to be doing on int128, uint128, and other non-primitive types, they all expose a property which allows you to get 1 or 0. There's not strictly a need other than consistency to also expose constants for 1 and 0 on these primitive types, but it's something where API review should make an explicit decision on, do we want to be consistent, and on any type that implements these numbers, we recommend exposing 1 and 0 either as a constant or as the property required by the integer types. Or do we say for the primitive types in particular, since they can use literals, do we not expose convenience properties for them? Noting that for primitive types like float and double, we do expose a number of constants, including for things like infinity, -0, nan, etc. And so my own preference is that we actually cover 1 and 0, but not the identities, just for consistency across how all types work, and we're not special casing the primitives.
I agree with you about not exposing the identities because that really is like an in the weeds numerics thing. 1 and 0, I'm trying to wrap my mind around when somebody might ever write byte.1 or byte.0 in their code.
So when you're thinking of it in terms of generic math, it will be frequent because it's correct to assume that the property returns a more performant value than doing the conversion.
Right, but is the generic going to end up binding on the const once the t's concrete, or is it going to bind on the interface?
It's going to bind on the interface, which will return a constant under the hood. When thinking more abstractly, it makes it more convenient to be able to copy paste code or provide concrete implementations if that's something desirable without needing to go in special case and change, for example, oh, I'm suddenly working with a primitive type. I can't use .byte or .0 or .1. I have to go and differ this implementation.
But I mean, but at the same point, if you write, the I enumerable of a number product, like you're going to start with multiplicative identity, and now like that won't. You already said you don't think that makes sense to expose. So I think it would be bad code if anybody wrote byte.1. Sorry, byte.one. So I don't see a reason why we would add them.
I mean, we could add them in the future if we wanted to. We do have a little bit of existing precedence for exposing what we would consider silly APIs in order to make like source generators' lives easier. For instance, like we added reverse Endianness of byte, which is literally just return this. And we did it in order to allow people writing, people writing tools which generate C# to not have to worry about special casing single byte integers.
And another benefit of 1 and 0 in particular is not just that, there are existing constants for 0 on like float, for example, because you have to also consider -0, but also that the natural type for the literal 0 is int. And so if you're calling an API which has multiple overloads, you have to remember to insert a cast to byte. And having cast to byte some literal 0 or 1 as compared to just byte.1 or 0 is potentially easier to miss and more complex to understand. It's very easy to miss that there's that implicit conversion and have the wrong have it accidentally go to the wrong overload.
Yeah, but then as soon as you use 2 or 3 or 4, you have the same problem, right?
Right.
Indeed.
But those are less common.
Yeah, but I mean, I don't know, if you write code and it appears, right? I mean, I think I understand the source generator argument. That makes sense to me. I also understand the generic concern. If you write generic code, it makes sense, but I think the average Joe that just, doesn't care about generic math and just pokes around in the type, I mean, I'm a bit concerned that we just overwhelm them with things that are either silly or just hard to understand, or a combination of both.
My view there is that it's no more silly than exposing 0 and 1 on big integer, decimal, and other types where there is a more efficient implementation. The primitive types aren't any more special in that sense.
Well, they are if they are literals, right? I think like for complex, we don't have, for example, like a literal representation, right? So for those, it would make sense, right? For things that have literal in the language, yeah, I think it will always look somewhat silly, including decimal, right?
Potentially.
Yeah, if we added these, I would definitely want to EB never them.
Well, yeah, this goes back to why you're adding them in the first place, right? If you're adding them for source gen, yes, then it makes sense. If you think, oh, it's just an advanced API, then I would say it doesn't make sense, because now you have to type it, but IntelliSense won't help you. And we know that people are really thrown off if IntelliSense excludes things because they think it literally doesn't exist, right? So it's a, yeah. I mean, I'm honestly of the opinion, like, we can start with not exposing them and then see how well we fare with that, and then once there's proven evidence that there is a real need for them, we can add them.
That sounds reasonable to me.
Yeah.
I kind of from here, I just have it listed as these members are explicitly implemented because they either conflict or don't make sense to expose. So max value, min value properties conflict with the constants. 1 and 0, if we were to expose, we would rather have them be constants than the properties, just because that's more efficient. The operator types, we want to defer to the IL implementation, and so those are all explicit. The get byte count and get shortest bit length are explicit, not implicit. That's not a strong preference on my end. users could, instead of using these, for example, use binary writers. But again, I don't have a strong preference on if these ones are implicitly exposed or explicitly exposed.
Can you give me like a quick rundown of like, why certain things are explicit, why certain things are implicit? Is it just because you think they're not, it's similar to the 1 and 2, which are 1 and 0, it's just not usable by themselves? It's usually just used from generic code, or?
Right. Things like leading zero count, we actually have places where they are required, or where the implementation is differing from anything else we expose. Because, for example, with byte, it actually operates on terms of bytes, not upcasting to int and then doing an integer operation, an int32 operation. And so it's very important that we have that. And then from a consistency perspective, it also applies because if you have int 128, you're going to have 0 and 1 and rotate left and rotate right, because they're not a built-in language primitive. The same goes for half, where it's not a built-in language primitive. And so do you want half to be different from single and double? And generally speaking, the expectation is no. Whereas for things like get byte count, this is a constant get shortest bit length, and the Endianness APIs are really only useful for serialization behaviors, or if you're working on it more generically. And so there was a slight leaning towards not exposing these ones, whereas these ones are just core mathematical operations, and so they do make sense to expose.
Yeah, that makes sense to me.
Yeah, well, I mean, things like the write methods here, it's, well, if the last 3 of them are dimming in terms of the first one, like if you don't go out of your way to make them be implicit, like you didn't even think of it as a choice. So it feels like, why would we write the line of code to intercept the method just to hide it? Just let the dim. I feel like we should, if we're dimming something, we should just let it float.
Okay, so you would lean towards exposing these APIs.
If we didn't have dims, I would say maybe we want to just keep having people use binary writer like we already have, instead of exposing a second way to do it. But it feels weird to say that we want to start policing things that we would dim, because you don't even get the compiler is not going to help you at all. It's, we add a new thing with a dim, it pops up unless we remembered to go to every type and block it off. So my feeling is once we have a let's call it a dim cluster, that cluster is like, fine, just leave it visible.
Okay, that makes sense to me.
It's just a forward consistency thing, because we're going to screw it up at some point.
Yeah, I was struggling with your argument why that's related to dims, but basically, I think this makes sense to me, because this thing is implemented in so many places, we will definitely miss.
Right. .NET 9, we add another overload to write little endian, and we don't remember to intercept that one on byte to make it implicit, or sorry, explicitly implemented, so it doesn't show up. And then somebody calls it, and then we go, oh, for consistency, we should go hide it, and now we break somebody. So let's just like that's where my long-term thinking's coming on that.
Static dims are so new that I haven't actually tried this. If you have a static dim, it shows up as implicit on the type?
No, it works just like regular dims, and it's hidden unless you explicitly make it public.
Right, so that I don't understand the argument, Jeremy.
Oh, so okay, I thought that dims would have floated as looking like they were implicitly implemented to IntelliSense.
No, dims are implicitly explicitly implemented, and you have to explicitly make them implicitly implemented to be visible on the type.
Okay, so it's actually the opposite. It's unless we go to the type and explicitly paint the method as being visible, it's invisible.
Yes.
In which case, yeah, making try write little endian be invisible seems That actually then seems the more natural, because why would we go paint everything as being visible? We already have binary formatter to do that work. So
for the unsigned types, copy sign, max number, and min number are explicitly implemented because they have no max number and min number have no behavior for integer types, and copy sign will be a no op for unsigned types because the sign is always 0. Likewise, absolute value is a explicit because it's a no op, as are the various is query APIs, which are always going to return a constant false, or in the case of is integer, true. Likewise, max magnitude is a no op because it's already the absolute value, so it's the same as max. And that's functionally how unsigned types work. You then have the same for character. Just the documentation for covering the interfaces or the APIs that are exposed by date only, date time. Decimal, there is an annotation that the existing -1 constant, because C# supports it as a constant, technically conflicts with the name -1. Conflicts meaning that there's two concepts meaning the same thing now. But -1 is the more natural name. And I would say that the name -1 was a mistake from .NET 1.0. And likewise, decimal has existing constants for 1 and 0, max value and min value. And then we would say no to the identity operations.
I mean, to me, exposing both -1 and -1 is just going to make somebody ask, what's the difference? So we shouldn't expose -1, and this type just has its -1 constant named wrong.
Okay. Then it also documents all the existing APIs and covers the operators being explicit. There's no real changes for any of the other types in terms of how that works.
Could I back up just a quick second? For system.char, can we say everything on there is explicitly implemented? Because that isn't really a numeric type.
C# treats it as a numeric type and allows you to do every single one of these operators, including rotations, shifts, etc., including using the add equals, etc. So it directly works on character. So as far as C# and
things like plus minus, yes, but like it's
multiply, divide, every single one of them works in C#, F#, VB, etc.
You really shouldn't be doing that.
But languages treat them as it. So this is functionally a character type, and we even have requests that we extend the vector types to support character as an underlying scalar type, so people don't need to deal with the conversion to U-short to do all the bit arithmetic and etc. that they're already doing.
But while C# allows a character, like character times 2 turns into an int.
Yes, but C times equals 2 keeps it as a char.
Yeah, because it'll truncate again.
As far as languages are concerned, as far as the JIT is concerned, as far as people want to use these types in arrays, vectorized logic, and general algorithms, character is, for all intents and purposes, a U-short with a few additional special operators on it that directly allow interpreting those bits as a character type.
What you should do then, if you really want to treat system.char as a true honest-to-God numeric type, is you'll also need to make runtime changes in order to allow like U-short arrays and char arrays to be cast between one another without using unsafe.as. Like I have a feeling that if we just start adding these interfaces to char without also doing the runtime work to make it like a true honest-to-God integral type, like we're going to be in a situation where people are going to get confused as to what this thing actually is.
Why would we need variance conversions between differing types? That's something that people don't want for ushort and short already.
Because it's a place where the runtime treats this type as asymmetric from every other primitive that's numeric.
Not really. You've got the only reason that short and ushort are allowed to convert between each other, or short and ushort arrays are allowed to convert, is because the runtime doesn't actually track whether it's assigned type or unsigned type under the hood. It roughly treats them as the same, except for when you're directly doing a type of check. As far as the stack is concerned, they are the same. Whereas for a character array, it actually tracks and always has tracked it as a different type, but has still supported every single operator on it as if it was a numerical type otherwise. There's no reason to change the runtime to allow conversion between a character array and a ushort array.
Going back to the original question, I fundamentally agree with Levi here. I think if you think about the vast majority of developers that are using char in the .NET ecosystem, they're not, while they might compare it to, numbers or do subtraction to do basic range checking, they're not thinking of it as a numerical type to the point where they'd want leading bit count exposed on char. If we're thinking about the use scenario of someone just looking in IntelliSense to figure out what they can do with char, like having all this stuff, I think is going to be a net negative for the general .NET ecosystem. Obviously, we can have all the functionality available explicitly for use when it's in a generic context. And if we start with it explicit, we can always add it as implicit later. But once we add it, we can't take it back. And I fear adding all this stuff is going to actually detract for the majority of .NET developers.
Yeah, I mean, so my preference would be char doesn't even implement any of these interfaces. But if it's going to implement it, then please don't make it look like it did.
Yeah, I don't necessarily mind if it implements the interfaces, but like to what Steve had just said, like char.is is actually a very common pattern for people to write today, because there are lots of is whatever static APIs hanging off of char. And if we start adding is canonical, is even, is finite, is infinity, and so on, like we're polluting an IntelliSense space that people actively and prolifically use today.
Okay. I don't personally agree, because when actually working with character types, it's very common, including for all those is APIs, to treat it as a raw set of bits and to do things like leading zero counts and rotations and sign checks.
For a very specific audience. I agree. Like when Tanner uses char, that's what he's doing. But 99.999% of developers using char are not doing that.
Okay.
These would still be as explicitly implemented. Like you could have T self equals char, correct, and everything should just work, right?
Yes.
Okay.
It would just be explicitly implemented and not publicly visible.
Yeah, and I think, if we decide that we regret that decision, it would be very easy to undo it going forward and say, hey, these things are implicit now for symmetry.
Okay.
But if you look through like APIs of .NET and look at char, like you'll see a bunch of is APIs already on there, and they're static.
Yeah. So I'll leave that as char should be moved to be explicit, but still implement them. For double and float, it's basically the same thing, with the only interesting thing being the same thing we decided previously, which is that pi on math is misspelled. It should be lowercase I, not capital I, which also makes it consistent with other APIs around pi we have exposed. And then it continues on for the rest of the primitive types, with there being an open question on, for here, should we also expose it for C-long and CU-long, which we did for infloat, because it was required for Xamarin, so they no longer need to maintain their own type. For all intents and purposes, C-long and CU-long are ABI primitives. They are numeric integer types. We have had requests from users to expose the operators on them. And so since we're doing this generic math push, it would make sense to just keep those in line and also onboard them as integer types.
I had to go look up what they were. It makes sense to me to just treat them as numbers.
Just so Jeremy, which commented in YouTube chat, I talked to Aaron a bit already about this, and he's the one that marked it as untriaged and in the 7 milestone. He and I had already discussed this to some extent and the reasons why it should be extended.
Yeah, that makes sense. I mean, it is a numeric type. Maybe not fundamental, but a numeric type nonetheless.
He and I also discussed it on the okay, Jeremy says he explicitly said he wants to talk, so we might want to ping Aaron if someone could do that, and then we can come back to that when he shows up, if he does.
So speaking of these types, it was mentioned earlier that there are some other types, like say SQL decimal in the framework. Do we plan on enlightening those with this, or are we really only talking about like the things within corelib proper?
We ourselves are only touching the things within corelib proper. Well, and the BCL in general, because big integer and complex are not in corelib, but
oh yeah, you're right. Okay.
Other libraries are free to implement these themselves where appropriate.
When you say other libraries, do we have anything that ships in .NET that might be interesting to implement?
I mean, SQL decimal seems to be one of them, but I don't know if that's one of the types that the SQL teams walked away from.
No, it's still around. We're still maintaining it.
But like it defines, operator plus for 2 SQL decimal values, etc. So it can probably get most of this. It has absolute value. For the most part, it's treated as if it's a number.
I mean, I think I've never ever done math on those types.
Me either. I pulled it up to see if it even defines anything math-like, or if it was really just the SQL database said this is called decimal, so now it has get me the .NET decimal and a couple conversion things, but they made it be a full number kind of thing.
Yeah, they implemented the null semantics, right? When you add stuff, you get back null, but
it's because it predates nullability in the framework.
Yeah, there's that, and then there's also the general thing that people extract the value, put it in the DTO, and then whatever the type ends up being, it's usually a regular int, right? Then you move on.
Right. I'm not saying, as Tanner said, we're not doing it. I don't know that I would even argue that they should do it, but this is a type that is outside the BCL that someone could do it to.
Yeah, I guess what I'm trying to get is like, do we have a list of types and have you made an explicit decision? Like, for example, the SQL types. Like things that ship in .NET is, realistically something we probably should really think about and then talk to the owners and make a decision.
That's been considered out of scope for what I was driving for .NET 7.
Okay.
The other types are free to implement and version them if they deem it appropriate and to drive it forward, but there's no reason or explicit need for us to do that or force them to. Aaron did show up, so Jeremy mentioned that you had some comments you wanted to have about this. I explained the rationale of why it should be exposed, having consistency with infloat, being generally on the track of these are ABI primitive types where people frequently want and need to do numeric type things, and so we've actually had requests from users to extend it even before infloat went up, but also in the infloat work items and discussions, people requested that we also extend C-long and CU-long. API review themselves had initially said that sounded reasonable, but then Jeremy called out that you had some additional thoughts you wanted to provide.
Yeah, thank you. So I get, to be clear, I get enfloat. Like I don't have any criticism. Like I can't argue with that. I think that you mentioned Xamarin has issues and there's a whole system with that. So nfloat has a long history that I agree we should just work with. I'm less convinced that C-long and CU-long have value. Like, they were added for a very narrow reason. They were added just for an interop, because of this weird C rules. And I guess I'm curious as to what mathematical operations does anybody think they're going to get in a supported cross-platform scenario? Because in some cases they're 32, and then in some cases they're 34. And it seems like you're going to have to special case them so much, any algorithm that is involved with them, because, oh, I have 64 bits. Oh, no, I have 32 bits. And so I'm dubious that they have a lot of value in anything other than a transport type.
It's the exact same considerations as you have in C itself when you are writing, for example, cross-platform libraries. Clang, for example, and LLVM use the long type in many cases. And so on Windows, it's 32 bits, and on Unix, it's pointer sized. But it's also the same considerations as infloat has. Infloat is a variable width type, where it is 32 bits on a 32-bit platform and 64 bits on a 64-bit platform. Native int and native unsigned int are variable size types that are 32 bits on some platforms, 64 on others. Big integer is a variable size type where even across operations, the size could change and the limits could change, and therefore how you want to operate with it could change. When you're doing interop code with these libraries, particularly if you're in the Unix space, and you're working with something that has been cross-compiled for Windows where they've not done the due diligence to go and change it to be, for example, int pointer of t under the hood to be consistent across all platforms, then you yet again have scenarios where you're doing integer arithmetic, and you often want to do that even with minimal overflow checking, doing checked addition, so that it performs correctly and you can do the correct error handling on the respective platforms. And allows you to have a consistent behavior within the confines of the normal arithmetic you're expected to do based on the inputs from that own platform.
So let me ask you a question. I mean, Aaron, if I remember correctly, basically the inspiration for adding these types and the creating these types is questioning the scenarios for them. So separate from the can we, there's the question of should we. You've enumerated some potential use cases, maybe for adding certain operators to these types, but that doesn't necessarily extend. Even if that's granted, it doesn't necessarily extend to everything on all of these interfaces. I'm wondering if this is another wait and see, where we actually see if after all this stuff is in use for a year, people have actually say, hey, here's where I need this, or are we just adding in another 100, 200 methods because we can?
So this is a case where I helped push for this because it's a scenario that frequently came up with cross-platform interop code, and I was one of the primary drivers who kept pushing on Aaron and Jan on we need something in this space because of how complex it is, especially when you start getting into those structs that contain nested structs that contain C-longs and stuff. Go ahead.
Well, I guess my point is I fully accept, like, the argument that you made about interop is 100. Like, I'm not questioning the interop need, to be clear. I guess I'm questioning all of the examples I heard from you were basically along one dimension. They are what is the architecture? It can vary, but in the C-long and CU-long, there's two dimensions. There's architecture plus platform. And that, to me, seems like we're trying to solve a problem that I'm not necessarily convinced can really be solved in a generic fashion. My point is, you're not going to be able to just plop C-long or CU-long into a generic algorithm, and it's going to work. You're going to have to special case, I'm on Windows as well. So your generic algorithm becomes less generic because you have to branch for what platform I'm on because I don't have as much scope for size.
Well, rather than scoping to platform, you just scope to the concept of max value or min value, because then it becomes the same consideration of a generic algorithm. Any type can have different limits. It can have a different min value, it can have a different max value, it can have a different, could even have no min or max value. So in the generic context, you write these algorithms in terms of checked arithmetic, which will detect overflow when it happens. And when you're dealing with existing inputs of T self, those will already be within the well-defined range. And then you also have the ability to detect the limits and ranges using min and max value to determine whether it's valid or in scope, and including doing saturation or truncation, depending on which one's relevant, if overflow doesn't matter. And so, for example, when you're doing interop code with, let's say, Klangsharp, you do have many APIs in libclang that end up taking long under the covers, generally to represent some kind of size. And so you already have to, when dealing with these things, you're manually having to go and write all this checked arithmetic to do things like basic multiplication, shifting, adding, etc., because you're having to extract it out into the if Windows, else Unix scenario. And this abstracts that away into a simple checked arithmetic-based API covering what all integer types kind of fit into. And of course, it's not just me that's asked for this. There was devs from silk.net that had asked for this on some of the APIs and various other cases where they've been asking for it because they're running into similar issues where they need to do arithmetic, but can't today easily because they have to manually extract out the long, do the cast to the platform-specific size, then do all the arithmetic in those two to three different paths, and then cast back up, where all implementations are functionally the same, with the only difference being what is the theoretical upper limit on when overflow could occur.
Go ahead, sorry.
I was going to say the libraries that you've mentioned, they're signed up to use this and use more than just the checked APIs?
Yes, they've asked for it, which is one of the reasons that I wrote up the proposal.
What is it? That's what I'm wondering.
C-long with full arithmetic support, because they are doing the various arithmetic operations and needing to do things like leading zero counts and trailing zero counts, all the things that you would do with normal arithmetic types.
I don't because I see it for C-long of, you're writing an iterator that's interoperating with C-long as the how many did it work through and what's your index. So I see it for plus and minus and 0. Everything else to me feels like this would not be a type that you would ever want to pick. I don't have a strong reason to say no. It's just I don't see the reason that you want Roddle and max number and what are you doing while doing interop with this thing?
It was designed, so the problem really is, as Tanner mentioned, someone has a signature and it's got a long in it, and shoot, I have to do all these weird things to pass down just what I want. So I get the interop thing, and I get some maybe add. I think that's what Jeremy's getting at. It seems, for an example, maybe this isn't fair, but I'm going to try it. This seems like, how many string types do we have in C++? How many integer types do we have in .NET? It very much feels like that's kind of, are there other types that we're going to be using in these very odd cases? Because I would hate to see C-long leak out of any type. It seems like C-long is a pure I would hope, is a pure implementation detail of any library. And I would hate to see them leak out. And I think enriching them further, that is the concern for me. I really don't ever want to see an API that has a .NET API on NuGet that says we use C-long. No, that seems wrong to me. And that's kind of, by making it a first-class citizen with all of this support, that's kind of what it feels like.
You would say the same for infloat, however.
So Enfloat, I agree with you. I think Enfloat, my position there is Xamarin already opened that up, so we're just supporting someone already. So that's why I have I'm far more accepting of that. And I guess I would hate to perpetuate that kind of idea. That's my opinion. I'm more than willing to defer if it really is a priority, but it just seems like it's an interop type, and elevating it to be such a first-class citizen seems like, oh, let's just use it everywhere. Or let's use it in places where aren't appropriate.
I would say it's not elevating it to be any more first class than Infloat is, or other ABI primitives are, because that's what it is. It's an ABI primitive type. And it being an interop services means that users generally shouldn't. But that also doesn't mean that users don't need to do things with it. And my feeling is that you wouldn't expose compare to methods or equatable methods on it or anything like that without also implementing the interface. So even if we said, we want to go and expose these operators because enough users have asked for them, that's not a reason to also say we shouldn't then just go ahead and do the minimal thing of implement the interfaces that correspond to that contract. We can recommend people don't do that, and the reasons why, but we shouldn't restrict them and say, we have feelings that you shouldn't use it like this, so therefore we're not going to implement the interface, but we're going to functionally implement everything the interface would otherwise require.
So I had a quick question, Tanner. Do you have scenarios where like native code might be taking buffers of these things rather than just individual scalar values? Because if so, I could imagine that we would also want to be able to put these into vector of t, which kind of no? Okay, never mind.
Vector of t very much intentionally only works with the ABI primitive, or with the runtime primitive types, not ABI primitive types. Partially because not all ABI primitive types are extensible or representable. But one of the core issues with C-long in a vector type is that it's not the kind of scenario where it's extensive enough you would want to vectorize it beyond what span already provides, and what span is already able to potentially optimize under the covers. We could essentially abstract that away. Whereas there are many cases where you need to do arithmetic of all sorts with it, especially where it's used as a size, because one of the most common operations is I need to compute this is taking the number of bytes of data, and so therefore you need to take size times 8, do some arithmetic on it, and then fit it into the right data. It's also used for things like alignment, where you end up having to mod 16 to round up to the nearest power of 2, or ensure that it's aligned to a 16-byte address, etc.
But where do you draw the line then? Like, I'm struggling with this halfway, I guess.
Well, that's what I'm saying. I'm saying it should be fully supported as an integer type, with the recommendation that users don't allow it to leak outside of the interop scope, and that includes that it shouldn't be used as for example, vector of t type. So that means that functionally you expose the operators that users interacting with this type need to correctly interact with it from a C# level, but you don't try and integrate it with the rest of .NET outside of that.
Do we honestly think that there is a real need for these?
I mean, I've got needs in my own code base, and I know that there's been other people who have requested it as well.
And converting it is not an option because we don't have a corresponding type.
Converting it to...
Well, it does seem like we could let conversion work. On int pitter / nint, we have the size property, or yeah, it has to be a property, because if it was a const, you wouldn't ever call it. It does seem like we maybe missed that on C-long. And so, if we told somebody C-long, its effective underlying size is 32-bit, like, fine, unsafe as it to int, and now party on. But we do seem to be missing where we know that data, we just didn't tell you.
Yeah, the main issue today is that you functionally have to operate on, you have to extract the value either to the individual type, so int versus inint, or you have to extract to inint, always do the arithmetic as inint, and then do the complex, potentially costly or complex conversion back. And that gets particularly difficult in cases of nested structs. And that's the reason why we actually went and exposed this type in the first place, which was because you end up having something that should be blittable, and should be what is functionally primitive, end up requiring complex and costly marshalling, which negatively impacts various platforms. There's effectively no good way to support cross-platform code without an ABI primitive of C-long. And then the remaining scenario is once you have a C-long and you need to do more than just transferring the data, like you actually need to pass some computed value to native, you end up having complexities and if else's that realistically you should just be able to interact with this as a integer type, and not have to concern yourselves about what the underlying representation is beyond that.
I'm just poking around in SQL, right? And so what I see in the SQL types is that effectively all the operators are used very close to 0 except for the comparisons. So, I mean, I'm kind of leaning towards, like, unless we have actual evidence that people need this type fully supported, I'd rather lean to say interrupt type, you convert it, you do your thing, you convert it back. And if that's not possible today because we're missing functions for that, then we should add those. But that seems like a compromise in between.
All right, I'll leave it as don't cover then, and then I'll let people who want it complain some more and convince Aaron that we do need it.
Yeah, I mean, my concern is it's like this never-ending thing, right? Where because now we do one thing and then we have to do another thing, and then it's like, because these interfaces are not necessarily small, and this is an area that we're actively investing in, and it's just busy work potentially.
I've already got a PR up that does it.
Well, yeah, for the current shape, right? But then you start optimizing it, and then you're like, oh, I need to optimize this type too, and
well, that's the neat thing about this and int pointer and most of the ABI primitives. You just defer to the underlying primitive type for the implementation. So it's a bunch of one-line methods that do nothing interesting.
I mean, I kind of disagree with Aaron in the sense that I don't think that this type will be attractive just by us adding the operators. It still has an ugly name. It still is an interrupt namespace, right? So it's not going to be, appearing super sexy, which I think is a good thing. But I'm more concerned about the long-term ownership cost of this by adding a bunch of operators where people, where there's like 6 people in the world that need them. That's kind of my gut feel. I might be wrong, but I'm willing to be proven wrong.
The interesting thing is it's not just 6 people. It is definitely a niche amount of people, but particularly 12. In the Unix interop space, long is the de facto type, and many Unix libraries have Windows ports, especially with WSL becoming more and more prevalent. There's often Windows ports and interop with Windows more directly for those libraries, and so long is really prevalent in that type of code, whereas it's almost non-existent on Windows because on Windows you just consider it the same as int32. And most Windows libraries don't go cross-plat, or if they do, they're keeping int32 or using the correct C standard types for fixed width.
What is the difference again between C-long and 32 then?
On Unix, C-long is equivalent to a native integer. So basically, when 64-bit, when it was just 32-bit, both platforms agreed that long was 32 bits.
I see.
when 64-bit came out, Windows said it is still 32-bit, and Unix said this is a handle size, and so it's the same as int pointer of t.
Yeah. The closest equivalent we have is actually not int32. It would be more like native int then.
Right.
Unless you're on Windows.
Unless you're on Windows, in which case it may be too big on a 64-bit platform.
Which I understand this because it's if you interoperate with C code that happens to be compiled with C long, then the end result is 32-bit on Windows.
Yep, and 32 or 64 bits on Unix.
But there's no representation in the bitness then, like I mean, ignoring size. Like, well, I guess I'm struggling to understand what the conversion cost is. It seems like bit splitting.
Because you, in order to most correctly support cross-platform, you either have to have two code paths, one for Windows and one for Linux, that effectively do the same thing, but one over init and one over int, or you have to have a code path that does everything as init, which means you may get you may get potentially incorrect results if overflow were to occur on Windows, and then you have to truncate down to int. So there's all kinds of minor nuances and weirdness that come about. It's the same issue that we had with int pointer and uint pointer before we had the language support for arithmetic. You have all kinds of weird edge cases where you have to consider things that the average dev is, even for the average unsafe or low-level dev, is potentially going to miss or forget about. And so having direct support for it makes it more cohesive, easier to use, and when you've got the integration with checked, then you can actually detect the overflows correctly, handling saturation, etc., where appropriate.
Yeah, that does sound like what Aaron described as the string problem, right? It's like, yeah, it's kind of close, except when it's not, and then you're completely screwed if you mess it up, right? It's yeah, that's unfortunate. Yeah, I guess the question is now, what happens when you wrap a library in .NET that uses C-long, right? At that point, you really have not a great option. Maybe.
Yeah, the option are either you surface C-long everywhere, which is what Xamarin did with infloat, which is generally undesirable, or you take inint in your public surface area, or even just int. You've got two options. Either you take int and you say, even on Unix, I'm going to restrict this to no more than 2 billion values, or you take inint and you explicitly do a checked. Basically, you check the argument range before truncating down to int on Windows.
Yeah.
Which is functionally what the constructors do, but that misses out on the nuance of when doing more complex arithmetic.
For those you're
such
kind
as
of
because
screwed,
you
right?
have an existing.
Like, I mean,
well, that's
and I mean, because the problem really is like, it doesn't even matter whether your library is, you know, C-long all the way. You know, the consuming code has to be C-long all the way. Right? So like that basically, now we talk about like, okay, can people actually write expressions that are typed as C-long, right? And the answer is sort of no, because, you know, the literals are all effectively natively typed to other types. And you insert casts everywhere, and then you could do them, but now the code becomes really ugly. So seems like you're always kind of screwed. That's just depending on where you are screwed effectively, right?
Yeah, it's a little bit better when you have the full support, because then you can just do C-long x equals 0, for example, because there's an implicit conversion from 0 to C-long, because that's always safe, because int always fits in a C-long. And then you can do most arithmetic as appropriate with correct overflow checking or saturation or wrapping as appropriate.
Yeah, so that assumes
size.
You're starting with variables that are typed as C-long, right, or parameters, right? As soon as you have just an expression with literals in them, then you would have to insert a cast somewhere, right?
No, because the literals implicitly convert to C-long.
No, I'm just saying, if you do let's say you have two numbers, you do a multiplication, right, and then you convert it, that's fine. But then the operation already happened outside of the C-long type, right? It already happened in int or in 64 space, right, depending on what your literals were.
Right, but it would only be implicit if it was int. If it overflowed outside of int, then it would
Right.
it involved any constant, then it would be outside the scope. And C# would say it's not a valid implicit conversion. You have to have non-constants involved and do something purely taking both int inputs rather than first upcasting to C long.
I guess if that's true, then I'm honestly struggling with seeing what the problem then ends up being. It just seems like you're kind of choosing where to crash, right? But it's just at that point it just becomes a function of like, well, you have a number that's too large, so physics applies. It just becomes now, you know, potentially different, like different design choices will result in different outcomes on where you detect that case, right? Either very early or very late, right?
Mm.
Which, you know, I guess if you overflow, like they have different pros and cons, but they all seem to result in some amount of non-working outcomes, right? So maybe it's okay. If you wrap everything in int and then just say, you know, only when you interoperate is when you truncate, and if that blows up, well, then you got an exception back, right? But yeah.
So like I said, I'm fine with, based on the feedback, just saying don't support them and then waiting for the people who are wanting this to go and complain.
Yeah. I don't know.
Yep. And then we're over time, but we're almost through. So if people are willing to stick around just a little bit longer, there's just the conversion API to go through for the generic math in general.
Will be just that applies to C long and C U long, right? That's the only two types.
Yeah.
Yeah. Okay.
Yep. So the create and conversion APIs are a bit complex. You kind of have three scenarios. You have two types in the same assembly, such as int32 and int64. They can know about each other, but can't know about types in deriving assemblies. So, for example, int32 can't know about big integer. In this scenario, you can only directly check for relevant types and do the conversions. You can utilize things like internal to expose details, allowing faster implementations, etc. The second scenario is you have a type like big integer, which can know about, once again, it can know about types in the same assembly, such as complex, and types in its dependencies, like int32 and int64. But again, if something was a dependent on system runtime numerics, big integer couldn't know about it. Then the third scenario is you have two parallel assemblies where neither depends on each other. For example, two standalone NuGet packages where the types can never know about each other unless one becomes a dependent on the other and therefore becomes scenario 2. So, you know, we've got these three scenarios to consider when we're talking about creating numbers or converting them. The first scenario kind of leads to the design we have today. You've got a create API. Users have to implement try create, and they would do it by explicitly checking for the types in the same assembly and doing the conversion and saying, hey, I can't do this if it's not supported. It runs into the issue where if the user passed in a big integer, it would fail. Whereas big integer itself can support all three of them. And you would use it exactly how it's currently proposed. In order to support the scenario of I have int32 being able to convert from big integer, you have to change the shape slightly. And so we end up with a different surface where try create is essentially implemented in terms of try convert from and try convert to. And it is not abstract. Users cannot override it. The reason for that is to help avoid circular dependencies, because otherwise it's too easy for try convert from to decide to call some other try convert from implementation or anything like that, and you end up with just, you know, a stack overflow. And so try create itself wouldn't be implementable by the user. It would be forced as this pattern, and then try convert from and try convert to would have documentation of these must be effectively self-contained. You can't defer to other convert from, convert to, or create methods. The implementation then looks something like this. You provide your try convert from, you provide your try convert to, likewise with int64, and then likewise with big integer. And the way this would work is the first thing it does is try create calls tself try convert from. So the first thing we do is we try and do what's effectively a constructor pattern, where we say, do I support what the t other is? And if so, directly convert the type, create my value. If that fails, that's where you fall back to t other try convert to. And so this is the case where it would fall back to big integer try convert to, where it would then be able to succeed if the type was supported. You still have the nuance of if two types are in assemblies that have no knowledge of each other, it can still fail. But the only way to satisfy that scenario is with this iNumber converter interface, where the usage effectively is this pattern. And so the general design is that we have a combination of pattern of scenario 2 and scenario 3, where for scenario 2, it covers the majority of cases. You are able to convert to and from the primitive types, to and from other common common integer types like big integer. You are even able to convert from arbitrary binary integers or arbitrary floating point numbers using the try write little Endian APIs, get bit length, radix, etc. So for example, int32 could support big integer abstractly by getting the bit length and then getting the lowest 4 bytes from that for truncation. And therefore, it can also support assemblies that it has no knowledge of more abstractly and performantly. But then you still have the issue of two types in assemblies that don't know about each other. And so that's where the iNumber converter pattern comes in. And so we're just defining an interface, a well-known interface that users can effectively take as another constrained generic for when that scenario is important, allowing effectively dependency injection, for lack of another word, by the consumer of the API to decide how the conversion happens.
We could, if we wanted to, make it work for wherever we put the Endian-based exports, right? Like, you could make ibinary integer. You could write a generic it can convert to any other ibinary integer by reading 1 byte at a time, shifting left 8, and oring in the value. It's not going to be efficient, but I don't remember if we had to go load your value from a byte representation.
Right, and we can provide a the issue is that we can't necessarily provide a dim for that because we that implementation is only valid if you have another binary integer. So a floating point type, for example, couldn't implement conversion from a binary integer as just left shift by 8 and or.
Right, but we could. I'm not saying that we want to, but we could make the non-abstract convert have a extra fallback of, well, if you're converting from and to if you're converting from a thing that has a binary representation, then
yeah.
You said shift is defined and or is defined, and I can now build this number.
Yeah,
but again, it would be
we could do that.
It would be in the case of big integer as opposed to the theoretical mutable big integer. That would be very, very inefficient.
Yeah. We could do that. The only open question I had on provided people believe this makes sense, believe it kind of minimizes the pits of failure, and I believe it does. The only open question is, do we just expose iNumber converter, or do we instead expose iChecked, iSaturating, and iTruncating number converter, or do we expose all 4? The only reason you might want the explicit checked, saturating, and truncating converters, or even just have iNumber converter expose 3 different interfaces there, is because otherwise a user can define any behavior. So for example, if we had links some method taken a T converter, without having explicit checked, saturating, or truncating versions, then a user could decide, I don't want overflow here, which is both good and bad. On one side, it gives users more customization on how conversion is treated and what's valid or invalid. On the other, a user could decide to an implementation may prefer to always do a checked conversion. Although, of course, a user could always provide a non-compliant implementation via injection.
Well, I mean, so how are we handling that for the types that understand each other? So ignoring the external converter, what's the position we ended up with now?
So we have create checked, which does overflow, create saturating, which does saturation, and create truncating, which does truncation. And then you have the try, convert, from, and to for each one. And the expectation is users correctly follow overflow detection, truncation, or saturation for each of these. And then the consumer of the API decides which one's appropriate.
Okay, but then you had with the convert to and convert from, what's that supposed to mean? Given that you already pointed out there are 3 different behaviors.
For which one?
Where you showed a sample of what big integer might do.
Oh, that was a simplified example showing just one API. In this case, it was just showing truncation. But for simplicity, I didn't spell out the whole thing. I called out in a comment. You have to provide, once for overflow, once for saturating, and once for truncating, not a single implementation.
Okay. I mean, it feels like we're saying conversion is these 3 operations. So yes. Maybe the late adapter has to provide all 3.
So iNumber converters should provide convert, checked, convert, truncating, and convert saturating.
I mean, it makes sense to me. It's saying when you do this, you kind of need to think about all 3 things. I could be convinced in other directions, but this seems like the starting place to me.
That sounds good to me.
I mean, everybody's welcome to write in throw new not implemented exception. Like, you have to make it compile. You don't have to make it work. If no one calls it, then no one cares. But
yep, that sounds reasonable.
So what is the final decision then? I think I lost the track of where we were.
So we'd have iNumber converter, but we'd have 3 methods on it. One is convert checked, one is convert saturating, and one is convert truncating. A given consumer will likely only use one, but a given converter should provide all 3. And there is no trying for these APIs because you're explicitly saying I support a T and a U.
Just thinking out loud, is there a way that we could instead only expose a try, convert, and you have to fit, and then we can write saturating, truncating, and checked in terms of that?
Not easily, because when you consider saturation, it's more than just truncation. You can provide a default implementation for saturating, to a certain extent. So you can do something like if the bit count is greater than max value, then return max value. But there's also kind of an issue there where floating point types, for example, don't really have a bit count. That's only valid for binary integers. For floating point, you instead have an exponent and a significant. And then you run into the general issue of you can't do a type check, a dynamic check, that is, against a interface constraint and effectively become more constrained. That's something which has been raised with C# LDM, but it's not something they have an answer for today. So if you're constrained to just where T is I number, and you can't say if T is actually binary integer, then I now have access to binary integer operations, and unless they're instance methods. But although get bit count is get byte count and get shortest bit length is instance, so maybe we could do something, but it'd require a little bit more thought on what that dim would be.
But I think the point a little bit is if you had a like the floating point types, because they have some loss of refined data depending on what their exponent's looking like, they have like, can I convert this precisely could return false, but you still don't quite know what the right answer is for truncation or saturation at that point, because you don't know if you want it to round up or down at the local limit. Is that right? Or am I misunderstanding?
Right, because you know the bit length, but you don't necessarily know if positive or negative means anything, or if or what direction it would be. You kind of have to know I'm a binary integer, and therefore positive and negative mean something, and therefore bit count plus positive or negative means I am lesser than the limit or greater than the limit. And you have to know what that limit is. Okay. And there may not be a min or max value available. For example, with big integer, there is none.
Okay. Yeah, I mean, so the hope that I was having there was if there's a way that we can get the numeric types to really just have to handle the degenerate case where something fits, is where the overflow, truncate, and saturate were they things that we could write a helper for on top of. But if the answer is no, then that's fine. I was just trying.
I've not been able to figure out something here. This is the conversion and creation APIs are the most complex part of generic math, because you're talking about creating an unknown type from another unknown type, and so there's kind of no good story for that, because it's you don't know what the types are, so it becomes a massively complex problem. And so this is kind of the culmination of trying to work through what the scenarios are, what the considerations need be, how we can handle them with the least amount of effort from the user. And most of the code a user is going to write is probably going to be some kind of some conversion logic.
That's fair.
And then that's the entire surface area. There's still the open question of, which really only needs to be answered for big integer, particularly of, do we want to, one, do nothing, or one, don't implement the generic math interfaces, which isn't really valid for big integer, but we could, two, leave the behavior as is, which means that conversions always throw. We could take a break and change the behavior such that the conversions no longer throw by default, but will in a check context. That's the same break we're taking for int pointer. Or three, we could say the existing public APIs retain their current behavior, and the checked versus unchecked difference only occurs in a generic math context, which we can do because we can have the public operator, but the interface contract be explicitly implemented. And so there just kind of needs to be a decision. And I'm leaning towards 3. We just take the break. We let people know if you're calling this in a unchecked context, you may no longer see an exception where you did before, and the fix is to wrap it with checked.
Yeah, I mean, mine's probably, if they're using the interfaces, do what the interface says, and if they're using the public type, do what it's always said. But I don't think we have the quorum to make this decision.
Okay.
I would agree with Jeremy, by the way, assuming we had quorum.
One of the issues there is just that with big integer, the only reason it overflows today always is because that was the only behavior you had possible. More concretely, when doing things with big integer, you want to be able to have both behaviors, and you don't want to have to go into a generic context to access those behaviors. And now we have the opportunity